Okay, in this lecture, we want to take the updated Lagrangian formulation, put it in its weak form, and do the FEA discretization. I'll just give you a heads up that I'm not going to work in the same level of detail for this as I did for the total Lagrangian because so much of it is the same. So I'm going to work pretty fast. That's why we can kind of combine both the weak form and the discretization into the same lecture. Okay, and ultimately I'm going to show you that the vectors that we come up with, the internal and external force vectors, are identical between the total Lagrangian and the updated Lagrangian formulation. Okay? Okay, so let's just say that formulating the weak form in the case where velocity is our dependent variable, remember that's how we developed the governing equations, utilizes what's called the principle of virtual power. Okay, so the principle of virtual power is the same as the principle of virtual work, except that the test function is going to be delta V instead of delta U. Okay? Okay, so let me just remind you of the governing equation that we want to solve, and this is going to be the momentum balance equation, right? So we ended up with the, here's our governing equation, right? The momentum balance said A times sigma, the partial with respect to C, plus rho A times B is equal to rho A V dot, and let's call that equation 1. Okay, so as with the total Lagrangian, with delta U, we're going to enforce that this test function delta V is equal to 0 along the area of the boundary where the velocity is defined. Okay, so as with delta U, we require delta V equals 0 on the boundary where the velocity is defined. Let's call that equation 2. Okay, so the development proceeds exactly like we did with the total Lagrangian and our principle of virtual work to obtain the following. Okay, and let me just remind you how we did that. We basically said we multiplied that equation by a test function, we integrated, then we integrated by parts to get the weak form, and we had this boundary term, and we'll end up with something that looks like integral from CA now to CB, right? Remember, we're using C because in the updated Lagrangian, our derivatives and integrals are with respect to C instead of X, even though we're still tracking everything with respect to X, our material point. Okay, so in that case, we now have the quantity delta V, comma C times A times sigma minus delta V times the quantity rho AB minus rho A V dot. Okay, and then that times dC minus delta V A T bar X evaluated on the traction portion of the boundary equals 0, right? That's the equation that we would come up with by doing the exact same procedure. Okay, so equation 3 in this case is the weak form, and it's a statement of the principle of virtual power. So, and then what we're going to do now is exactly like what we did for the total Lagrangian. We see sort of 3 distinct terms, right? We have this term that looks like delta V, comma C times A sigma. We have delta V times rho AB, right, which is sort of kind of a boundary term. It's a body force term. We can combine that with our boundary term, and then we have delta V times rho A V double dot, and we come up with an internal, an external, and a kinetic portion of, instead of work, we'll have power. Okay, so let's just say, like the total Lagrangian with work, we're going to define the following virtual power terms for internal, external, and kinetic. Virtual power. Okay, and when we do that, let's say we have then that the delta P, which is the total virtual power, is equal to delta P internal minus delta P external plus delta P kinetic is equal to 0. Call that equation 4. Okay, and then we can say that we can define then delta P internal in a very similar way. We can say this is the integral from CA to CB times delta V comma C A sigma dc. Right, that's our first term. We can define delta P external is equal to the integral from CA to CB of delta V times rho A B dc plus the quantity delta V A T bar X on the traction boundary, gamma T. Okay, let's call these equations 5, equation 6, and then finally let's go ahead and write equation 7 as the kinetic term. Okay, that's going to be equal to integral from CA to CB times delta V times rho V dot A dc. Okay, we'll call that equation 7. Okay, we're going to discretize now in the exact same way that we did for the total Lagrangian, except now instead of interpolating the displacements, we'll interpolate the velocities, okay? Right, so we would say that our velocity, and remember, we care about the velocities at the material point, so that's x and t, is going to be equal to the quantities n, which are functions of x, right, transpose times our nodal velocity vector, which could be a function of t. Okay, and similarly for our v dot term, now that's which is our acceleration, right? We have n of x transpose times now the v dot, the acceleration, the nodal accelerations, right? Okay, and we also then can define our strain measure, right? So we define that strain measure as dc. Now that's going to be equal to n, which is a function of x, times to the transpose. But now this is going to be comma c, right? So we're taking the derivative with respect to the current coordinate. So we must have some variable transformation to be able to do that. We'll talk about that. Okay, and then this becomes VT. And I guess I could put these are element level, just to remind you, these are nodal velocities. Okay, and we would define that as B, right? This is how we have done this in the past. Transpose times V is a function of t, right? Where B is the derivative vector. Okay, so let's go ahead and call these equations 8, 9, and 10. Okay, and I will note here, okay, note that this B is different than the B naught that we had in the total Lagrangian form, because here we're taking the derivative with respect to C instead of the derivative with respect to X. Okay, okay, so now if you remember how we proceeded with the total Lagrangian form, we proceed in the same fashion. We define our virtual power terms in terms of a virtual velocity conjugate. Okay, and it turns out because we're now dealing with power instead of work and velocity instead of displacement, that conjugate value is still a force. Okay, so we end up being able to write delta P internal is going to be equal to delta V transpose times this force vector Fi internal. Okay, call that equation 11. Delta P external, you can see where this is going now, is equal to delta V transpose times F external. And I should probably remove the I, since that subscript doesn't have meaning, since I'm drawing these in putting brackets around my vectors, right? Let's call that equation 12. And then we have delta P kinetic is going to be equal to very similar delta V transpose times F kinetic. Okay, let's call that equation 13. Okay, so now we just do exactly the same thing as we did with the total Lagrangian. In this case, we're going to equate equations 5 through 7 with equations 11 through 13. And we're going to get the discrete equations for the updated Lagrangian formulation. So we have the term here that dc is going to be equal to this term, let's say B transpose times VE, right, where that's our velocity of the element. Call that equation 14. We have that F internal is going to be equal to the quantity, the integral from over. I'm going to write this now. So let me write out, I guess, what it in one form, and then I'll transfer it to the other, and then use the other throughout. So we had CA to CB times, right, N comma C times sigma times A dc, and we're going to take A dc and say that's area times incremental displacement. That's an incremental volume now, and so we can say this, we'll call this B d omega to tell us it's over the volume. This will enable us to write the 3D case a little more easily. Okay, and so I can write this then as, let's just say, the integral over the volume, and I'm going to go ahead and make my substitution. This is B, right? The partial of n with respect to C is B, so I'll just say this is B times sigma d omega. Okay, let's call that equation 15. Okay, similarly for the external, I'm not going to write it out as explicitly now. The external can be written as the integral over omega times rho n times b d omega. Okay, and then we have our boundary term, which looks like n times a times tx bar, evaluated on the boundary where the traction is applied. Call that equation 16. And then we have our kinetic term, right, where we could write in a similar fashion. We have M, our mass matrix, times V dot, right? Okay, and I'll just say that's where we define M, where M is going to be equal to the integral from omega times rho n transpose d omega. Okay, and we can use our we can substitute with conservation of mass, and if we use the conservation of mass, we can write this in our original coordinates as rho naught, so n times n transpose, okay, d omega naught. We'll call that equation 17. Okay, so when we do that, what you should note is that equation 17 is the same between the total Lagrangian and the updated Lagrangian. Okay, so the mass matrix is the same for either case. Okay, and what that leads to is a governing set of equations that looks like, right, M times V dot, right, plus F internal, right, is equal to F external, right? And we could similarly write that as what's V dot is U double dot. So M times U double dot, right, is going to be equal to F external minus F internal, which is equal to F, right, the net. We call that equation 18. And what do you see is that it's the exact same set of vector equations as we had for the total Lagrangian formulation. Okay? So you might be thinking, well, that sounds great, but you didn't really prove that the internal and external forces are identical. So I'll do that for the case of the internal force. I'll leave the external force as an exercise for you. So let me just give you some remarks here on that. Okay, so number one, the first remark is that the internal and external forces in the updated Lagrangian and in the total Lagrangian formulations are identical. Okay? Which is what I kind of told you, but we just now have to show that. So here we go in the updated Lagrangian case, right? What did we have? We had that I'm going to now write it in vector form just for convenience here. Let's say Fi internal, right? So the internal force vector, Fi, is equal to the integral over omega, the volume, times n, right? I, comma, c, right? Times sigma d omega. And so let's go ahead and write this out now in the 1D case that we're working on. This becomes integral from Ca to Cb, and this is still ni comma c sigma, and now we have a dc. Okay, let's call that equation 19. So that's what our internal force vector for the updated Lagrangian looks like. Okay, what do we know? Well, but we know that the partial of ni with respect to c, right? We know what's n defined on. N is defined on the material coordinates x, right? So we can't, this can't be derivative can't be taken without resorting to the chain rule. So this must be the partial of ni with respect to x times the partial of x with respect to c. What is this? That quantity is, if you remember, that's 1 over f, where f is the deformation gradient. Okay? So I can go ahead and write equation 19 with this change of variables. So we can write 19 as follows. We can say that, so Fi internal is now equal to the integral from Ca to Cb of, let's see, this quantity looks like ni comma x, right, times sigma times a times dc over f, right? Okay, so what do we know that is, so let's think about, recall what's the definition of f, right? Right, so we defined f formally as dc dx, right? So dc over df is dx. Right, so this quantity here is dx, which is our change of variables. So that quantity then goes to xa. This quantity then also goes to xb. Okay? I want to remind you of something else when we were defining stresses several lectures ago, when we talked about the relationship between the nominal stress and the Cauchy stress, right? So I'll just say, recall also, right, that we said that sigma times A, the Cauchy stress times the actual area, is equal to the nominal stress P times the initial area A naught, right? So we can just make that direct substitution, right? And now we end up saying that Fi internal is equal to the integral from xa to xb times ni comma x times p a naught dx, right? What's a naught dx? That's d omega naught, if you want to put that back in a volume term. So I can now say integral over the initial volume of ni comma x times p times d omega naught, right? Let's call that equation 20. Okay, equation 20 is the total Lagrangian form, right? So this is important here. Equation 20 is the total Lagrangian form of F internal. Okay, so what that means is that we just proved that the total Lagrangian and updated Lagrangian internal force vector are identical. Okay, and I'll just say, you can go convince yourself if you are interested, we can do the exact same thing with the external forces. So I'll just say that you can show that the external force vector is also equivalent, and you need to, let's just say, is also equivalent via the conservation of mass, which you'll have to use, right? Plus the above change of variables. Okay? So what this means, the upshot of all of this, is that the total Lagrangian and updated Lagrangian are two methods for expressing identical quantities. Okay? And they lead to the exact same discretized equations. Okay? So then you might be going, well, that was a colossal waste of my time. Why did I even care about the updated Lagrangian? And it's exactly for the reason that I told you before. It's simply a matter of convenience. It matters how we want to define our constitutive law, how we can even measure our constitutive laws. Sometimes we measure them with respect to the current coordinates. Sometimes we measure them with respect to the original coordinates, okay? And sometimes we can even mix and match these. Okay, so let me write that down. So the selection of updated Lagrangian or total Lagrangian is simply a matter of convenience. Okay, and the selection can even be mixed and matched. Okay, kind of a colloquial. Part of the reason I want you to be aware of these things is because as you go out and now you start reading maybe some papers on people's formulation for different physical phenomena, I don't want you to think that, I want you to be aware, I guess, of why they might choose one over the other. If somebody develops an equation on the basis of principle of virtual power and you're only familiar with the principle of virtual work, you need to understand what they're doing, whether it's equivalent or not. And so I'm trying to paint that picture for you here. Okay? The third comment that I want to make is that when we developed the updated Lagrangian, we used V, the velocity, and sigma, the Cauchy stress, as our dependent variables for the updated Lagrangian. And we used U, the displacement, and P, the nominal stress, for the dependent variables for the total Lagrangian. Okay? These selections are not intrinsic to the formulations, right? We could have selected others. We could have done the total Lagrangian with velocity and the updated Lagrangian with displacement. Okay? The key was that we were using a different coordinate system for taking our derivatives. Okay? So these selections are not intrinsic to the formulations. Okay, and all I mean is that we could have selected others. Okay, and the final thing I want to say is that, as you might expect, because we have the exact same set of equations, the application of the boundary conditions and the assembly of our global equations is identical between the updated and the total Lagrangian. Okay, so assembly and application of boundary conditions is identical between the two formulations. Next lecture, I'm going to talk a little bit about the mesh distortion and how important a one-to-one mapping is in the element. So we'll talk about that in our next lecture.